Hi everyone, this is Vipin Kumar here. Welcome back to my YouTube channel, and in this video I'll be discussing the solution of numerical problems of flight mechanics from GATE Aerospace 2020. And if you are preparing for GATE Aerospace 2021, then this video can be very useful for you and your friends who are preparing for GATE Aerospace Engineering. So you can share this video with your friends also if you find it interesting. Okay, so in this video I'll be covering the solution of the problems as well as the concept associated with the problems. So with this, let us move to the problems now. So here you can see I have collected problems from GATE Aerospace 2020. So question number 12, question number 21, 25, 31, 41, 45, 46, 54 and 55. Total 9 questions are there. So out of these 9 questions, first 5 questions will be covered in this part of the video, and remaining 4 questions will be covered in the second part of this video. So with this, let us start. So question number 12, for conventional airplanes, which one of the following is true regarding roll control derivative and yaw control derivative? Where so CL delta R, C and delta R, both control derivative are taken in the context of rudder deflection. Okay, so first let us take C and delta R, which is the yaw control derivative. So C and delta R is change in yawing movement coefficient with respect to change in rudder deflection. Okay, so this is we need to understand first what is the sign convention of yawing movement. So this is the tail, this is the airplane. So if airplane is taking a yaw in this direction, so that is taken as positive. Okay, so to take this positive, what kind of rudder deflection is required? That is important. So this will be the yawing movement to move the airplane in this direction. To generate this yawing movement, there will be a side force in this direction. Okay, so side force in this direction, if let's say I take the top view of this rudder, and this kind of side force will be generated when rudder is deflected in negative direction. So this is negative as per sign convention, this is taken as positive as per sign convention. So for negative rudder deflection, there is a side force in this direction, which in the combination of tail moment arm generates a positive yawing moment. That is why for change of delta R and negative, there is change of delta Cn positive. That means Cn delta R is less than 0. So if we look at the options, option A and C are correct and option B and D are incorrect. Now let us discuss CL delta R, which is the change in rolling moment coefficient with respect to rudder deflection. So if let's say this is an airplane, this is being the right wing, this is being the left wing. So the sign convention for rolling movement is positive in clockwise direction. Okay, so when it is positive in clockwise direction, so that means delta CL is positive. Okay, now if we analyze the same with respect to change in rudder deflection, so for that we have to look at this. This is the rudder. If this is deflected in this direction, so there will be a side force in this direction. If this is deflected in this direction, there will be a side force in this direction, and in this direction the deflection of rudder is taken as positive. Okay, so for positive rudder deflection, there is a side force in this direction, that means towards the right wing. So side force towards the right wing, if this is the CG location of the airplane and this is the vertical distance between the CG and the line of action of side force, then if side force is denoted by F and this vertical distance is Z, then there will be a rolling movement in the positive direction, that means F into Z. Okay, so for positive deflection of rudder, the positive rolling momentum is being generated, that means CL by delta R is positive. Okay, or CL delta R greater than 0. If we look at the options, so you can see here CL delta is greater than 0 and CN delta less than 0 are in the option A, so option A is correct. Now question number 21. Velocity of an airplane in the body fixed axis is given as 100 minus 10 and 20 meter per second. So this is x velocity, this is y velocity, this is z velocity. The side slip angle is, so we know that side slip angle is the angle between the plane of symmetry and the resultant velocity. So if resultant velocity is from this direction, so this angle which is denoted by beta is the side slip angle. Now this is, let's say, the the resultant velocity. So we have three components of velocities. So resultant velocity is Vx square plus Vy square plus Vz square. Okay, so 100 square plus minus 10 square plus 20 square is around 102.64 meter per second. So this is 102.64 meter per second, and there is a velocity in this direction which is minus 10 given here. Okay, so from this vector diagram, if I take sine beta, so it is V by V. This V is nothing but this is U, this is V, this is W. Okay, so from here beta is sine inverse of minus 10 upon 102.64, which is around minus 5.6 degrees. So this is the answer of question number 21. Then question number 25. An airplane of mass 5000 kg is flying at a constant speed of 360 km per hour at the bottom of a vertical circle with radius of 400 meters as shown in the figure. Assuming that the acceleration due to gravity is 9.8 meter per second squared, the load factor experienced at the center of gravity of the airplane is. So we have to find out load factor here, and it is very clear from this diagram as well as from the numerical that it is a pull up maneuver. Okay, and we know that for pull up maneuver the expression for turn radius is given by v square upon g into n minus 1, and in this numerical we have to find out n minus 1. So n minus 1 is equal to v square upon gr, or n is equal to v square upon gr plus 1. That means n is equal to 360 km per hour, so in meter per second it will be 100. Radius is 400 meters plus 1, so it is 2.54 plus 1, which is 3.54. so this is the load factor experienced at the center of gravity of the airplane in a pull-up maneuver. So 3.54 is the correct answer here. Now next question is question number 31. So in question number 31, for three different airplanes A, B and C, yawing moment Cn values are given for different values of beta. We have to find out the true statement regarding directional static stability of airplanes A, B and C. So when we talk about directional static stability, so C and beta is the parameter which determines the stability. So Cn beta is positive for stable aircraft in yaw. That is why we need to find out Cn beta for all three airplanes. So first, for airplane A, so Cn beta is dCn by d beta, or delta Cn by delta beta for this case, because we have the finite values here. So 0.03 minus 0.03, this minus sign is there, 5 minus minus 5, so 0.06 divided by 10, which is 0.006 per degree. So this is Cn beta for airplane A. Similarly for airplane B, so for this airplane B is 0.025 from here, minus 0.025 divided by 10, so 0.05 divided by 10, which is 0.005 per degree. And now for third airplane, this is airplane C. So Cn beta for airplane C is minus 0.040 minus 0.040 divided by 10. Okay, so that is 0.08 divided by 10 minus 0.008. So here you can see Cn beta for A and B both are having positive values, where Cn beta for airplane A is higher than Cn beta for airplane B. That means both are stable, but airplane A is more stable, whereas airplane C is unstable. So if we look at the options, we can see here this is incorrect, this is also incorrect. Airplane C is unstable, airplane C is unstable, so both possibilities are there. But when A and B are stable, with A being more stable, so this is the correct answer here. This is incorrect. Okay, now next question is question number 41, which is the last question of this first part of the video. A wing of 50 meters span with elliptical lift distribution. So B is given. Elliptical lift distribution means Ostwald efficiency factor is 1. Lift is given as 80 kilonewton, which is this. Velocity 90 meter per second. Density is 1.2 kg per meter cube. Induced angle of attack at this condition we have to find out. So we know that induced angle is given by this formula, CL upon pi EAR. Okay, so CL upon pi EAR. So we know that CL is L upon half rho V square into S. Okay, if I put this value of CL in this equation, so it will be twice of L divided by rho V square into S multiplied with this pi EAR. Okay, so E being 1, if I put the values 2 into 80,000 divided by 1.2 into 90 square into pi, E is 1 and AR is what? B square by S. So this B square by S, if let's say I write B square by S here instead of AR, so this S is cancelled, so into B square, so B square is 15 square. So when I put all the values, the value of alpha I in radians will be around, let me calculate, uh, 2 into 80,000 divided by 1.2 into 90 square into pi into 15 square. So it is 0.023 0.02328 radians, and in degrees it will be 0.02328 into 180 by pi degrees, which is equal to 1.334 degrees. So this is the induced angle of attack for the given conditions, 1.334. Okay, so this was the last question of this part. Okay, so with this I'll stop this video and would like to request all of you, if you like this video, you can share this with your friends. And second part of this video will be covering question number 45, 46, 54 and 55. So that will be released soon. So for now, let me stop this video and thank you all of you and take care.